Okay, so we're going to have a quick look at covalent bonding in this and discuss bonding in some molecules like carbon dioxide, oxygen and nitrogen, and we're also going to have a look at things called sigma and pi bonding to see how electrons are shared in orbitals. So the first one is covalent bonding. So a bit of quick revision, that single bonds contain a single pair of electrons, which is just 2 electrons. So for example, in this example here, you can see that there is 2 electrons shared between oxygen and hydrogen. So that would equate to 1 single bond. You also have another single bond here. So when you're drawing this out, it would look like this: oxygen with hydrogen on either side. So a single bond is a pair of electrons. Same thing with ammonia. You can see it in ammonia here. There is a single bond there, a single bond there, and a single bond, because one of those electrons is belong to hydrogen, and one of those electrons, so this electron will probably belong to hydrogen, and this electron will belong to nitrogen. So in this one, you end up having NH3. Now the shape is slightly different than what you see there, but we'll come to the shapes later on. Same thing then applies then for methane. So you can see this single bond here, a single bond here, because it's a pair of electrons being shared. Again, in each of those single bonds, one of the electrons, let's say this one here, belongs to the hydrogen, and this one here would belong to the carbon, and it's the same all the way across. So you end up forming a single bond all the way around with the hydrogens. In a double bond, you've got 2 pairs of electrons shared. So in this particular one, you can see here, there's going to be a double bond formed. So 2 of these electrons belong to oxygen, which are those 2 there, and 2 with the X's belong to carbon. So when you're drawing this, you're going to end up with a single bond, which represents this one here, and then you're going to end up with another single bond underneath, which represents this one here, and that totally gives you a double bond. And then of course it's the exact same on the other side, a double bond as well. And then finally, the third one that you've got to look at is nitrogen. So we've got 1, 2, 3 pairs of electrons that are shared. So nitrogen forms a triple bond. So a couple of things to note. First of all, when you have a single bond, a double bond and a triple bond, an assumption that is made is that a triple bond that you would find between a nitrogen molecule is 3 times stronger than a single bond. And that isn't the case, and we're going to see why in a couple of minutes. We've just had a look at nitrogen in terms of a Bohr diagram. Now what we have to do is actually look at it in terms of orbitals and how these electrons are set around the orbitals, because obviously they don't exist in definite radii from the nucleus. So what we're going to do is we're going to redraw nitrogen, except we're going to draw it in orbital form. Now I'm only interested in the outer electrons. So for example, you can see generally in a Bohr diagram, the first shell, n equal to 1, is always capable of holding 2 electrons. But those 2 electrons are not involved in bonding. We're actually only interested in the outer shell. So when we're looking at nitrogen, nitrogen is number 7 on the periodic table, which means that it's got 7 electrons. Now out of those 7 electrons, 2 electrons are on the n equal to 1, or the first shell, and then the other 5 electrons are on the n equal to 2, which is the outside shell. Now it's the outside shell that's involved in bonding. So for the following diagrams, we're actually not going to be looking at the inner shell at all. So realistically, all I'm going to be looking at is the 5 electrons in the outside. The first thing we're going to do is look at nitrogen, is its electronic configuration. So nitrogen is number 7. So its electronic configuration is 1s2, 2s2, and then 2p3. We can break this down further as 1s2, 2s2, and break it down into its individual orbitals. So we've got the 2px orbital, we've got the 2py orbital, and we've got the 2pz orbital. And remember that an s orbital is a sphere. And then a p orbital is what's called a dumbbell shape. But again, it's 3-dimensional as well, like this. and then your electrons are found in those. Your s orbital can hold 2 electrons. So this can hold 2 electrons. So basically your 2 electrons are in there somewhere. So let's say there's an electron there and an electron there. And most of the time that's where they're going to be. In your p orbital can also hold 2 electrons. So let's say there's one there and one there. Now that would be just an example of a p orbital. That's one single p orbital. Let's say that's the py orbital. You can also have the px orbital. So the px orbital is like this. And you would also have 2 electrons in there. And you can also have the pz orbital. And the pz orbital, let's say, is running along the z-axis. And you can have 2 electrons in there. So each p orbital can hold 2 electrons. But the p sublevel, in other words, all of them together, the p sublevel can hold 6 electrons when you put all 3 of them together. So that's just some revision of those p orbitals. Now back to nitrogen, what we've got is we've got 3 electrons that we've got to put in. So the 3 electrons are separated into px, py, pz, and they fill them singly first. So we put an electron in px, we put an electron in py, and we put an electron in pz, and there's our 3 electrons. And it is this particular one that we're actually going to be dealing with here, and this is the one we're going to be drawing. If we were to draw this fully, you would start with 1s2, so you would have your s orbital like this with 2 electrons, and that would be your 1s orbital. And then you would have your 2s orbital, which will be surrounding that. So you again have, you know, another one, and there's another 2 electrons. But because there's 2 electrons and these are full, we're actually not interested in these at the moment. We're only interested in the orbitals that are involved in bonding. And for nitrogen, it's the p orbitals. So the p orbitals then would join all the way around like this. So there's your px, there's your py, and then your pz will go across this way. So we're actually only going to be drawing the pz's because the diagram gets a little bit confusing at that point. So drawing out the py's, we're going to then fill in our electrons. So I'm going to draw a quick diagram and I'll be back. So here we've got our orbitals drawn out, the p orbitals. And again, these are only the ones on the outside. So we've got px. So px here is in yellow. So that is the px. Your py is the one in blue. And then you've got pz, which is in green. And remember what we're trying to draw here. We're trying to draw nitrogen 1s2, 2s2, 2px1, 2py1, and 2pz1. We're not drawing the 1s2, 2s2, we're only interested in the p's. So this means we've got to fill in 1 electron in the px orbital. So we're going to pop in 1 electron there. We've got to pop in 1 electron in the y orbital. So again, it doesn't really matter, we'll pop it up there. And then we've got to fill in 1 electron on the 2pz orbital, which is going to be there. And this basically is the distribution amongst the p orbitals in nitrogen. So this is one nitrogen atom. On the right hand side we have another nitrogen atom, and these two are going to bond. So again, same thing. We're going to have 1 electron in the px, we're going to have 1 electron in the py, and we're going to have 1 electron then in the pz. So I'll put that one back there. Now remember, electrons want to pair up here. So what happens is the px on 2 sides, so this whole atom here is going to overlap with this. And how well you can see this, but as you drag it across, you will get a certain amount of overlap. So I'm going to drop this one here so you can see it. And let's have a look at the overlap. So the overlap occurs between a couple of things. So the first thing you have is an overlap amongst the px ones. So we'll draw that in there. You then have an overlap between the y. If you keep overlapping them, I can't draw them here on the screen. And then you have an overlap between the pz's. So the pz's go all the way across to there. So now what we're going to do is we're going to have a look at what type of overlaps you can have. So there is a couple of overlaps. The first one that you can have is what's called a sigma bond. So a sigma bond is a head-on overlap. And a head-on overlap could be an s orbital and a p orbital, and these two cross over. So when these two are crossing over, you end up with an overlap that looks like that, and you get this space in the middle, and that's the overlap part. You can also have the same thing happen with two p orbitals. So there's one p orbital, there's another p orbital, and again the same thing. You take one of the orbitals and you start to overlap, and you can see then that there's a significant overlap space in there. So in terms of head-on overlap, you get a sigma bond, which is quite a strong bond. So now what we have to do is look at our nitrogen molecule and see, have we got any places where there is a head-on overlap? Well, there is. There's one here in px. So where these two overlap, you are going to get a sigma bond. So this one here is a sigma bond. There is no other head-on overlaps. So the next one that you have is what's called a pi bond. So in a pi bond, which is the other type of bond you need to know, you're going to get a sideways overlap. And a sideways overlap looks like this when you have p orbitals crossing over each other. So we do one p orbital like this, one p orbital like that, and then as you grab them, they will overlap. So when they overlap like that, you get two areas that are overlapping. So you get this particular part here, and you get this particular part. The amount of area that's overlapping in a sigma bond, so this area of overlap and this area of overlap, is actually much greater than the area of overlap in a pi bond. So the sigma bond is, let's say, strong, and the pi bond is less strong or weaker. So let's see if we can find some pi bonds in our diagram. So pi bonds is where they sideways overlap. And I think you can see here that looking at the py, so your py is this top one here, this is going to be a pi bond, this one here, because when they cross over, they're going to go sideways. And the same thing with the pz. Your pz's also go sideways, so this is also a pi bond. So what you ultimately have between nitrogen is you have three pairs that are shared. So your first pair is along the p-axis, so you can put in a bond for that. So there's a bond right there. You have another bond between the y orbitals. That gives you another bond. And then you have a bond between the z orbitals, which gives you a third bond. But these bonds, one of them is a sigma, one of them is a pi, and the other one is a pi. So you have a sigma and two pi's. Because the sigma bond is stronger than the pi bonds, that means that the nitrogen molecule at a triple bond, it can't be 3 times as strong. Normally in a single bond, so if you bond something like C to H, if there's only one single bond, it's a sigma bond. So in order for nitrogen to be 3 times as strong in its triple bond as carbon-hydrogen, you would have to have 3 sigma bonds, which you don't have. So the pi bonds are weaker, which makes a triple bond not 3 times as strong as a single bond. The next one we're going to have a look at now after nitrogen is oxygen.